the story of the famous Isaac Newton sitting under an apple tree. The man did more than just discover the three laws of motion. Newton found that although it was easy to represent and calculate the average slope of a curve, the slope of a curve was constantly changing, and there was no way to give the exact slope at any one individual point on the curve, or the slope of a tangent line to the curve at that point. In 1666, Newton and his contemporary Leibniz, though independently, calculated a derivative function f prime of x, which gives a slope at any point of a function f of x. This process of calculating the slope or derivative of a curve or function is called differential calculus, or in Newton's terminology, the method of fluxions. He called the instantaneous rate of change at a particular point on a curve the fluxion, and the changing values of x and y the fluence. As a core concept of calculus in modern mathematics, derivatives are used throughout many careers and real-world problems. Let's see how derivatives can be applied.
Businesses use derivatives when calculating the prices needed to maximize their profits. Take an ice cream shop, for example. At $3.75 per cone, they find that 5,000 cones will be demanded. But for every 75-cent decrease in the price, 300 more cones will be demanded. At what price and quantity will their revenue be maximized?
We construct the price function for this product by doing p minus 3.75 over q minus 5,000 equals the change in p over the change in q. Because it's decreasing in this situation, it would be negative 0.75 over 300, which equals negative 1 over 400. We then multiply q minus 5,000 to both sides, which leaves us with p minus 3.75 equals 1 over 400 times q minus 5,000. This equals 25 over 2 minus 1 over 400 q. We then add 3.75 to both sides, which essentially leaves us with PQ equals 65 over 4 minus 1 over 400Q. The revenue, therefore, is, equation-wise, RQ equals QP times Q, which in this case would be 65 over 4Q minus 1 over 400Q squared. To find the marginal revenue, we find the derivative of this, which would be 65 over 4 minus 200Q. We then set this equal to 0 to find the critical points, which we find to be 3,250 equaling Q. As a side note, we find that the second derivative of RQ equals negative 1 over 200, which is a local max. In conclusion, we find that Q equals 3,250, which yields a maximum revenue at which price is P 3,250 equals 65 over 4 minus 3,250 over 400, which is $8.13 approximately.
Wow, that's so expensive. It's like salt and straw on crack. And now you have the scoop on derivatives.
Calculus can be used on the soccer field too. Have you ever been watching a game and wondered how far or high the players can kick the ball? Well, Isaac Newton figured out a way to do that too. Derivatives can be used to find the height, velocity, or acceleration of a ball at any given time, given a function, or vice versa. Consider this problem. After a good save, the keeper in a soccer match brings the ball to the edge of the goal line for a drop kick. The ball follows the curve s of t equals negative 0.1 t squared plus 2.5 t, and it travels several feet forward before it nears the ground. What is the maximum height that the ball reaches? And what is the velocity when it comes into contact with a 6-foot-tall player for a header?
To start off, we rewrite the original function, s of t equals negative 0.1 t squared plus 2.5 t. Then, using the power rule, we find the derivative, which is equal to negative 0.2 t plus 2.5. To find the x value of the vertice of the parabola, we set the whole function equal to 0, so that 0 equals negative 0.2t plus 2.5. Then we bring t to the other side, and then we divide the whole thing by 0.2, so that t equals 12.5 seconds. Then we plug that value back into the original function, s of 12.5 seconds. After plugging 12.5 in for t, we get negative 15.65 plus 31.25, which gives us our answer of 15.625 feet, the maximum height that the ball reaches. To find the answer for the second part of the problem, we begin again with the original function, which is s of t equals negative 0.1 t squared plus 2.5 t. We set the function equal to 6, which is the height of the player. Then we move it to the right side so that the whole function equals 0. Now we will use the quadratic formula, negative b plus or minus square root of b squared minus 4ac all over 2a to find our t values. We get the values of 2.7 and 22.3 seconds, though we will use 22.3 seconds because we know that the ball is decreasing in height after 12.5 seconds from the previous problem. We plug that value in to the first derivative function of s of t because that will give us the velocity. We get negative 4.46 plus 2.5, which then cancels out to be negative 1.96. Our final answer is that the ball is traveling at negative 1.96 feet per second when it comes into contact with the 6-foot-tall player.
In this situation, calculus was applied to find the travel height and velocity of the ball so that the receiving player could adjust his or her position for the header.
All passenger plane crashes in the Himalayas, and the first response team must get there as quickly as possible. The helipad is located directly 30 miles west of the crash and 23,760 feet above ground, and there's a downward wind of 15 miles per hour. If the helicopter's max speed is 250 miles per hour, how long will it take the helicopter to reach the crash?
Alright, so we're going to begin by drawing a picture here. So we have our plane crash on the bottom right, and then to the left we have our helipad, which is actually 23,760 feet above ground. And there's C there, which is what we're trying to find. And then on the bottom we've got our helipad is 30 miles to the west of our plane crash. And we're going to have a 15 mile an hour downward wind, and the maximum speed of our helicopter is actually 250 miles per hour. Alright, so first we need to convert the 23,760 feet into miles so that we have the same units. So we're dividing by 5,280, which is how many feet are in a mile, and we get 4.5 miles there. And next we're plugging that into the Pythagorean theorem to get what C is. Alright, so we get the distance of C is 30.34 miles. Alright, so the next thing we're going to do is apply the operator to both sides of our Pythagorean theorem. And we're doing this to figure out what the speed of C is. So once we apply the operator, we're going to get 2a dA dt plus 2b dB dt equals 2c dC dt. And we can cross out the 2's because we know that those are all going to cancel themselves out in the end. So next we're just going to plug in our values here. So we have a equals 30 times dA dt, which is 250, plus 4.5 times negative 15 miles per hour equals 30.34, and we don't know what dc dt equals yet. So now we're just going to solve for dc dt. Alright, so we have 7,500 minus 67.5 equals 30.34. And dc dt, the speed of our helicopter with the wind, equals 244.974 miles per hour.
So the first thing we need to do is convert this to miles per minute, because remember our final answer needs to be minutes. So to do this, we're going to take 30.34 for the distance of c divided by 244.97 for the speed of c. This will cancel out the distances and give us 0.1239. This is a fraction of an hour in time, so we can put this into minutes. We're going to do 0.239 times 60, because there are 60 minutes in an hour, and this gives us our final answer of 7.43 minutes. 3 very different examples were just used to demonstrate the use of derivatives. Thanks to Isaac Newton's brilliant mind, a method has been found to solve these kind of problems.